Make sure that you write down all of Dalton's atomic theories. He was the first one really to kind of have some guidelines on how we can identify what the elements are, the basic building blocks of all of our compounds. And he was kind of the forefather of all the modern chemistry that we do today. The one thing of all the things he wrote down is this one right here we're going to take a look at in this chapter, because it turns out that not all atoms of a given element are identical. Now at his time there was no way to look at the radioactivity and breaking up an atom, so this was pretty earth-shattering at the time. But right now what we know is that there are different isotopes of atoms, and they actually do have their nucleus can differ by the number of neutrons they have in the nucleus. So we know now that this isn't exactly true, although for all practical purposes it doesn't matter if they differ that much in the nucleus with regard to neutrons. They still are going to act the same. So in that case they are pretty identical. So that's just the one thing you want to know about Dalton's atomic theory, the one thing that isn't quite exactly how he put it. Everything else is good. The second slide didn't show up on this, but it's the law of multiple proportions, and honestly it is not on our test. It is something that we'll talk about in later chapters as well if it shows up on our final exam from St. Cloud State, but right now don't worry about the law of multiple proportions. As we go through and we write some of these formulas, make sure that you are writing the symbol correctly. So it's either a capital letter or it's a capital letter and a lowercase letter. One of the two. It's never two capitals, and so you should be careful how you write that. And if we want to indicate how many, it's a subscript. So this indicates that there are 2 chlorines and that there's nothing there, but it's indicated that there's 1 calcium. Later on in the chapter we're going to write charges up as a superscript, like a +2 or a -1, that kind of thing. And those charges can be written there, but ultimately what you see in the book and you write in the homework and all that stuff are the subscripts here that indicate how many of each kind is there. Okay, so the first thing we want to talk about is the structure of the atom. How did we know the structure? I'm sure you know what the structure is. We know in there is a nucleus with protons and neutrons, and then on the outside of the nucleus there are some electrons. And so we kind of have that idea of the atom, but where did that come from? Well, J.J. Thomson was the first one, and this is what he is known for, is that he found that all matter emitted these tiny negative particles, and he did an experiment involving a cathode ray tube. And there is a picture in the college textbook that we have in the room, but ultimately what happened is he came up with these negative particles called electrons. Well, they also knew from previous experiments that the atom is neutral, so obviously there has to be some positive particles, and we call those protons. And in a neutral atom, they balance each other out. Lord Kelvin, another scientist of the time, came up with an idea. Because once they knew that there were negatives and positives, they wanted to know, well, how are these arranged? What's going on here? And so Lord Kelvin, maybe at dinner time, came up with this idea of plum pudding, and you're probably thinking, what is plum pudding? It's kind of like raisin, like bread pudding or something like that. You have a whole bunch of little raisins scattered throughout, and a whole bunch of little electrons scattered throughout. And this isn't exactly what he postulates, but it's the idea that we have a scattering of positives and negatives, and they balance each other out. So in this case we have 4 negatives and 4 positives, so there you have a neutral atom. And they're just scattered all over the place in the atom. So that was an idea. Well, to check this out, so Rutherford actually decided to test out that hypothesis, and you should look on page 64 of your textbook as you write this, write these notes. And what happened was that there were 2 observations and conclusions from this experiment that are very important to understand. So here's a picture of what's happening, and we see here that there is a source for alpha particles. Now just to realize that alpha particles are big, heavy, positive particles. And you do need to know that they're positive to understand what happened here. Then what happened is these particles were shot at this gold foil, which of course had a whole bunch of gold atoms. And then the resulting alpha particles were able to be detected on a detector on the other side. Once they passed through the gold atoms, they were able to be detected. And so basically what we're doing is we're shooting positives at atoms. So if you think about what should happen is that the alpha particles, half the time, they should be hitting positives and bouncing right back, like, you know, positives and on a positive. And then half the time, the positives should be attracted to the negatives. So you should kind of see a 50-50. If they're truly just scattered randomly throughout, you should see a 50% chance that they'd stick, 50% chance they'd bounce. Well, that's not what happened. What happened was that most of the alpha particles passed right through the gold foil. And that conclusion was that really there's just nothing there. If they passed right through with no detection or, they didn't deflect at all, the atom must be mostly empty space. And this has been confirmed many times since then. As an example or an analogy, if the nucleus were the size of a grape, the nearest electron would be a mile away. So kind of think about that analogy there. You've got a lot of empty space in atoms. Now the second conclusion is that very few, the alpha particles were strongly deflected back. Rutherford said it was like shooting a gun at a piece of paper and having the bullet bounce back. So the conclusion there is that there must be something that it's hitting, an extremely dense, positively charged nucleus. Of course, you're shooting positives at it. So if it's being reflected, or deflected, I should say, it's obviously hitting something positive. It's repelled by it. The other thing is that it's strongly deflected. So we must be talking, it's hitting, like a brick wall. So what they came up with is the density of this thing later is that you could take the nuclei from atoms. If you could do that, if you could work through all the space and just get the nucleus, you can make a small pile of it, the size of a pea of just nuclear material, it would weigh 250 million tons. So that is an incredibly dense material. So you think about radioactivity or atomic weapons, you can see the incredible power there. So what does the atom look like? They determined there's this extremely dense nucleus that contains protons, positive one, and neutrons with no charge. That came along later. There is a relatively great distance away electrons with a negative charge of -1. Now, do distinguish between charge and mass. The mass of the atom comes from the protons and neutrons. These things are very massive compared to electrons. Electrons have virtually no mass at all. In fact, if you lose electrons or gain electrons, it really has no effect whatsoever on the mass of the atom. So definitely look at page 65, there's a little table, and realize that the electrons have nothing compared to protons and neutrons. Now, that does not mean that the charges are different, because protons have a charge of +1, electrons have a full charge, -1. Okay, so they have equal opposite charges, it's just that the masses differ. The other thing to walk away from this video with, though, is that electrons determine a substance's chemical reactivity. They may have virtually no mass, but they do have that -1, and they are the ones that is going to determine a chemical reactivity. Keep this in mind, super important. In a regular, normal, high school, even college lab, you are not going to touch the protons and neutrons. You're not going to touch that nucleus. All you're ever going to do is mess with the electrons.